So we're going to continue on in chapter 13 with something called a power series. So just a reminder here that when we have a geometric series, we should be able to find a sum with that. Okay. And from this one, we should recognize that first of all, our first term is what? It is 1. What's the common ratio? Oops. Guess we should have studied that more then, shouldn't we? It is, of course, x. Now, they've already told us that the absolute value of x has to be less than 1, so they've already said, hey, this is a geometric series that will converge. So if we want to write that series, this will be, of course, f of x equals, our first term is 1, and then we're just going to multiply that by x to get our second term, and multiply that by x to get our third term, multiply that by x to get our fourth term. Now that could go on and on and on forever and ever. And you can see from the pattern, this is just x to the n power, or we can write it as the summation from n equals 0. N equals 0 will give me the 1 right here, so that does work out to infinity of x to the n. Now, if you look at this expression, it looks like a polynomial with infinite terms. But there really is no such thing. Okay? A polynomial has to stop. It has to have certain degree to it. So we call this thing that goes on forever and ever with x's to an infinite power, we call this a power series. Or you could say it like this. It's a series of powers of x. And then remember that this interval that we have convergence is called the interval of convergence. We know that only when we choose x values between -1 and 1 will that series converge. And then if we choose polynomials from this, those polynomials, like if I just chose the first 3 terms or first 4 terms, those would be called partial sums. What we did in previous chapters. So this says, let's go ahead and graph the first partial sums. Now what they have already represented here are the, is this graph of 1 divided by the quantity of 1 minus x. So that's what the graph would look like if we were to graph the first partial sum, which of course is just that first term there. And we can write it as s of 0, so when n equals 0, we get 1. And of course, that's just this line that looks like that. That's our first partial sum. It's just the line y equals 1. Yeah, really didn't show me much, does it? Okay. Let's take a look at our second partial sum when n equals 1. That's just going to be the first 2 terms here, which is just a line that has a y-intercept at 1 and a slope of 1. And so it's going to look like this. That one. goes like this. And you might even notice that that's a tangent line there, isn't it? Okay. At least it sure looks like a tangent line of the graph. It is intersecting the graph. Okay. And then, if we go to our next partial sum, the s sub 2, this is actually a parabola. And we know with a parabola, we can find the vertex by doing, remember it's hk, and h is always the opposite of b divided by 2a. The opposite, in this case, of b, and see it's actually in reverse of what we would write back in, say, Algebra 1, where this is a, b, and c. So the b value is 1. The opposite of that, of course, is negative 1. And our a value is 1 times 2, so we get 1/2 for that. And then if we substitute that h value in for x, that'll give us the y value, our k value, okay, which in this case would be 1 minus 1/2, which would be 1/2. Negative 1/2 squared is 1/4. Add that to 1/2, and this would be 3/4. Okay. So if we go to the left 1/2 and up 3/4, right about in here, and then graph this parabola, this parabola would kind of look a little bit like this. That is our second one. And our third partial sum, you could see, is x cubed. X cubed is going to act like a snake, and I'll kind of sketch that in here. That's going to look a little bit like this one right here. So I'm going to go through, go down, and act like that. That's our fourth partial sum when n equals 3. And then, if we did this s sub 4, it's going to look a little bit like this. It's going to kind of have that parabolic shape. It's going to look a little bit different because it's going to be an x to the 4th. Now, all of these are actually going through this same point. That's pretty easy to see. When x equals 0, all of these terms are going to be 0. It's just going to be 1. So we know that all of them are going through that same point. Okay. Do want to take you to a graph that will hopefully show this a little bit better. We've got it somewhere in here. Calculus. Anybody see it? At least I thought I had it here. Oh, I guess we better log in. Hello. So let's take a look and see how this guy looks. Intro. Yep. We'll go look at this guy right there. Okay. So again, this is the graph of this rational function. Of course, this was our first partial sum, second partial sum, third partial sum, fourth partial sum, fifth partial sum. Now, why are we doing that? Okay. Well, if you remember back from AB calculus, remember zooming in? Okay. And in that AB calculus, you just zoomed in on the original graph and the tangent line. Okay? You said, hey, they are locally linear. Remember when you use that word, that term, locally linear? Okay? That means that this original graph approaches a linear function right here. But notice what happens here if I do a second degree. Can you see the difference between these? It might be hard for some of you to see. I'll make it a little bit thicker there for you. But can you see where we're actually getting closer to the graph when we change from the tangent line equation and then do this one that's a second degree power series? Now what if I use the third degree power series? Can you see where now it's matching it even closer? We've got a longer range that it looks like pretty much it. And now when I go to the fourth one, you can see it going up here to the right, there's really, you can't distinguish between the two of them. Okay? We have increased it all the way from here to here, whereas when we had our tangent line equation, this one, it was only good in this small range here. Okay? So, why is that important for us to understand? Because, wrong thing, what we're going to do is use these series and make sure, or use those to approximate our curve. So the point here is, notice the partial sums of higher degrees approximate the curve closer. And you can see, if I want to get even closer, I'll take it to the 7th degree. Even closer, I'll take it to the 20th degree. Okay? If I go to infinity, what do you think? I'm going to have that curve. Okay? So, let's take a look at another one here. Let's have this function here. They say g of x is this. Okay? So, you can see that g of 0 is pretty easy to find. It's kind of similar to what we had before. All of these terms have x's in them, so those are all going to be 0. So g of 0 is just going to be 1. Now, if I took the derivative of this, what would I get? Well, what's the derivative of 1? Anybody got that? Derivative of 1 is 0. What's the derivative of x? 1. What's the derivative of, if I have x squared divided by 2 factorial, what's that going to give me? Derivative of x squared is 2x divided by 2 factorial. What about the next one? What's the derivative of x cubed? 3x squared divided by 3 factorial plus, of course, the next one would be 4x cubed over 4 factorial plus, and even if we did this general term, we know that this would be n times x to the n minus 1 divided by n factorial. Well, wait a second here. Put our dot, dot, dots. I think we all can see that this does simplify to what? 1 plus, what would be 2x divided by 2 factorial? Oops. Do we need a reminder of what factorials are? Because you're scaring me here. 2 factorial. One of our Nathans, tell us what a 2 factorial is. 2, right? 2 times 1. So what would 2x divided by 2 factorial be? X. And then what about this one? What about 3, bless you, x squared divided by 3 factorial? What's that going to give us? Anybody? X squared over 2 factorial, right? Because remember, 3 factorial is 1, oops, times 2 times 3. 3 divided by 3 gives us 1 there. So yes, this will be an x squared over 2 factorial. What about this one? What's this going to be? Our next term. What's that going to simplify to? Yes, again, we've got 4, and 4 factorial is 1 times 2 times 3 times 4. 4 divided by 4 is 1. So yes, this is x cubed divided by 3 factorial plus dot dot dot. And won't even this general term also be this one right here, x to the n minus 1, and then if we factor out the n out of the n factorial, won't we have n minus 1 factorial? So wait a second here. What does g prime actually simplify to? It's the same thing, isn't it? Didn't we already start out with 1 x squared over 2 factorial, x cubed over 3 factorial? So yes, we can see from this that g prime of x equals g of x. Okay, big stretch. It's attached to a brain cell somewhere. What graph is g prime always equal to g? What graph, if you take the derivative, is the same graph? Go ahead.
E to the x.
E to the x. What's the derivative of e to the x?
E to the x.
What's the derivative of e to the x?
E to the x.
What's the derivative of e to the x?
E to the x.
Are you going to just go for on forever and ever every time you take the derivative? If I take and do the second derivative, won't I still get that? So, guess what? This series is actually a series that represents e to the x. This function that they defined as g of x is actually e to the x. So, this thing here, this polynomial, will represent e to the x. Okay. Take a quick little pause here for us because, again, trying to make sure we understand the significance and importance of it. Remember when we looked at this graph? Where'd it go? And how it got closer and closer and closer. Okay? We have a polynomial. Polynomials are pretty easy to deal with, right? You just put in an x value and you either take the first power, second power, third power, fourth power. Aren't those pretty easy calculations for you to do? Okay? What is e to the x thing? Remember, e is a number that goes on forever and ever and ever and ever with no repeating pattern. Okay? Could you imagine trying to program that number into a calculator or a computer? Okay? You have somebody who started as soon as computers were made, typing in digits, and would still be typing in digits and still would not be close to the end of it, would they? Okay? So, your calculators don't have e to the x stored in it. Okay? Your calculators and computers use these series to approximate those. Okay? Much easier calculations, right? Think about how easy a calculator could be just taking and doing x squared, x cubed, x to the fourth, x to the fifth. Just that same number, multiplied, multiplied, multiplied. Okay? So, that is the significance of this thing that we're dealing with right now. So, let's take a look at another example here. Okay? This says, let's go ahead and construct one of these polynomials based upon these conditions that they've shown here. Okay? So, first of all, it says let's use this polynomial. Let's set this polynomial up. So when x equals 0, we get 2. Well, think about that. What's that telling us in this polynomial, p to the x? P of x. Isn't that giving us the constant term right off the bat? Anything with any power, x to any power, when we put in 0, it's going to go away. But if we have a constant term, that's what's going to be left here. Okay? So that's 2. Now, for some reason, they don't give us any other points, but they give us all of these derivatives at 0. So let's think about, let's even kind of look at this last one. Okay? Remember, if we take the derivative of this as it is, what's going to happen to this 2 when we take the derivative of the 2? It's going to be 0. It's going to go away. Okay? And then, think about it. All of the terms that still have an x in it, what are going to happen to those? Good. Going to go to 0. Now, which ones, when we take the first derivative, will still have x's in them? X squared and above, right? Derivative of x squared is 2x. Got an x in it. X cubed is going to be a 3x squared. Still has an x in it. Which one will be a constant value? The one that has what? X to what power? First power. So really what they're telling us when they give us this, they're actually telling us that the coefficient of the x to the first power has to be 3, right? Because the derivative of that will give us 3. Okay. Now, let's take a look at our next one. I think I should have 5 as the coefficient of the x squared, right? Ooh, but wait a second here. What happens when I take the first derivative? What's the first derivative of x squared going to be? First derivative of x squared. 2x. Which means the second derivative is going to be, as I've written it here, not 5, but 10, which means I should have what in the denominator? 2. Would you mind if I put it as 2 with the little factorial behind it? Okay, and that's still going to be 2. I think you can probably see why as I go to the next one. We know if we're doing the x cubed term that we want this coefficient to be 7. But wait a second. How many derivatives am I going to have to take before I get this to that constant 7? How many derivatives am I going to need to take? 3. But won't that be 3x squared, then 6x, and then 6? So what do you think I need in the denominator? 3 factorial. Okay. And now I think you see what the pattern is. On the fourth one, we'll do 11x to the fourth divided by 4 factorial. Because we take that first derivative, it'll be 4, second derivative will be times 3, third derivative will be times 2, the fourth derivative times 1. 4, 3, 2, 1. Okay. And all the way up to this fifth one would be a 13, x to the fifth divided by 5 factorial. Yeah. So what we end up with is, this one, of course, is a polynomial of the 5th degree. It has 6 terms in it. Okay? And if we wanted to write the general series of this, we could say, I'm going to use a capital T here, and I'll use a little n in here. And if I wanted to, I could put like a 5 here because we're going to the 5th degree. Okay? But if I wanted to write this, every single one of these terms, I could write it like this. A sub n some constant times f, and then I'm going to put in parentheses a little n there, and that's anytime we see parentheses, if you recall from AB, that's not telling us that it is a power, p to the fifth power, but it's saying it is the fifth derivative, the fourth derivative. So this is the nth derivative times x to the n all over n factorial. A again is some constant like 13, 11, 7, 5, and 3 that may change each time. The derivative is in here, and then x to the n, and then divided by n factorial. This is what's called a Taylor series. Taylor, bless you, series. Okay. So, let's backtrack a little bit and make sure we have some good understanding and knowledge of these terms that we're going to talk about. All right, so first of all, a power series. What is a power series? It's any polynomial with infinite terms. Again, the weird way we're saying it's a polynomial, even though we know a polynomial can't be infinite. Okay, but it's a power series because you can see that every single term has x to a power. That makes it a power series. This one doesn't shift left or right. It is centered at 0, just like y equals x squared is a parabola that's centered at 0. And of course, if we wanted to change it to shift it to the right, we could do something like that. That's this idea of, okay, this one doesn't have any quantity of x minus 1s in it. Okay, so it's centered at 0. Okay, a type of power series called a Taylor series, the one we just did, if it is centered at something other than 0, a of course could be 0, but a is any number, you'll see that because it's centered at something at a, we do add in here an x minus a in each one of these. Okay? That's the idea that we are centered at something other than 0. Okay? And then you'll hopefully see a pattern in this, that we have this derivative derivative of the function evaluated at a. That shows up here, 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 and here. Okay. Now this one you can see doesn't have that in parentheses, so this is just like it's the 0 derivative. What's the 0 derivative? It's the original function. You just evaluate the original function at a. Then you take the derivative of the function, evaluate it at a. The second derivative, the third derivative, the fourth derivative, the nth derivative. And then, just because of that pattern that we saw with our denominator, you'll see that the denominator is going to be n factorial. Okay? N factorial. 2 factorial because this was to the second degree. If you wanted to add this in here, you could put a 1 factorial. Of course, 1 factorial is just 1. And then you would even put this one as a 0 factorial. Of course, remember, 0 factorial equals 1. And if you wanted to complete it, I guess you could put the x minus a to the 0 power, which is 1. Okay? So that is a Taylor series. Big idea. We're going to do a ton of Taylor series. Taylor series, Taylor series. Now, if you were a really cool guy like McLaurin, and you wanted to kind of say, hey, Taylor, you're pretty cool, but I want to be cool too, then what you could do is say, hey, wait a second, I'm going to take this Taylor series and I'm just going to keep it centered at 0. In other words, a equals 0. We're not going to shift this at all. And I'll write the same thing down without any x minus a's. I'll make sure I publish this, and just by doing that, I'll name it after myself, and I'll call it the Maclaurin series. Does that seem pretty chintzy? Kenneth, anybody ever steal some of your work and put it as theirs with their name on it? Probably. Maybe.
Yeah.
When you kind of feel like, man, I did all the work. All you did is put 0 in for A, and now your name is in every textbook. Like, really? Shouldn't it be like Taylor 2? Rather than, come on, really? But, hey, yeah, I guess it's who you know. Who you know. Got his name on it, forever, famous. So, Maclaurin, exact same thing. Exact same thing, except we've got 0. We're just centered at 0. All right? So, all Taylor series are power series. Because every single time you have a Taylor series, you have x to a power in each term. Okay? But this is a unique type because notice up here, these may or may not have this derivative thing in here. They may or may not have the n factorial in the denominator. So some of the power series will be Taylor series. That's only if they follow this pattern. Reminder, a Taylor series has infinite terms. A Taylor polynomial will have a finite number of terms. In other words, a Taylor polynomial will always be a partial sum. It's going to stop somewhere. You can kind of imagine that our calculators are going to do partial sums. They're not going to go forever and ever, right? They're going to approximate it. Okay. So, this one right here, you can see it is a power series. X to the 0, x to the first, x to the second, x to the third, x to the fourth. Because the denominator goes 2 factorial, 3 factorial, 4 factorial, this is also a Taylor series. Why is it a series? Because you took the time to put the plus dot dot dot. If you don't take the time to put the dot dot dot, you either made a mistake or you were answering this and saying that this is a Taylor polynomial. Of degree 4. It could also be referred to as a fourth partial sum. Might be written as T sub 4 or S sub 4 or P sub 4. Depending on the professor, depending on the book, depending on whatever video you watch. Some use T because it's a Taylor series, some use S because it's a sum, some use P because it's a partial sum. Whichever one you want to do, I'm not too particular about it. Okay? So, reminder again, Taylor polynomial of degree n for x near or centered at 0 is this Maclaurin series. Let's just write this out so we get used to this. Okay, this is going to be the original function at 0 times x to the 0 power. That's 1. Yes, I know it is. all divided by 0 factorial. That's 1. Yes, I know that is. Okay. Do I need to write those on there? No, again, I'm just trying to write this to see so we get used to our pattern. The next one will be our first derivative at 0 times x to the first power divided by 1 factorial. Our next one will be the second derivative at 0 times x squared all over 2 factorial. Next one will be our third derivative at 0, x cubed divided by 3 factorial, which again, for a Taylor polynomial, okay, Taylor series, or Taylor polynomial of degree n, this then would be f, and then in parentheses n to show that that is a derivative, x to the n all divided by n factorial. If it is a Taylor polynomial, that's when I stop. If it's a Taylor series, then I'll put a plus dot 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 dot. Does that make sense? Yeah. All right. Let's take a look at this. Let's do a Taylor polynomial of degree 1 to approximate some function f of x near 0. When we do that, notice what this will be. Taylor series of degree 1. Well, I'm going to, I want to write it two different ways. I want to write it starting with this guy up here. This would be f of a plus f prime of a times x minus a Doesn't that look pretty familiar to you? You seen that before? What is it? Isn't that our tangent line equation? Believe it or not, you were actually doing Taylor series in AB calculus, even though Taylor series isn't a topic that's tested in AB calculus. You did, every time you did a tangent line, you did a Taylor polynomial of degree 1. Okay? So, if we were to put this where x equals a, or, I'm sorry, if we center this near 0, then that's implying that we want a to be 0. And if that's the case, then this would be just f of 0 minus f plus f prime at 0 times x. All right, let's take a look at this. We've got our cosine graph right here, looking absolutely fabulous. And it says, let's write a Taylor polynomial of degree 1 to approximate this. Okay, so remember, our Taylor polynomial is of degree 1 will be f of a plus f prime of a times x minus a. Since they use the term here near x equals a, or x equals 0, that's telling us that we want to make a equal 0. Okay. So, in order to do this, of course, we're going to do f of 0. That'll be our f of a. I guess I'll write it out here one more time just so you see when a equals 0. This will be f of 0 plus f prime at 0, and then of course x minus 0. All right, so if cosine is our function, what's the cosine of 0 going to be? Anybody? It is 1. And then our derivative of this, of course, is going to be negative sine. Negative sine of 0 is, of course, 0. So when we substitute this in, this is actually pretty lame, isn't it? This is just 1 plus 0 times 0, or just 1. Our tangent line here is just the line y equals 1. So, if we wanted to estimate the value of our function using this, we would say that f of 0.05 is approximately equal to our tangent line equation at 0.05, which is going to be 1. That's pretty lame. How about at 0.4? Well, it's still the same thing. Okay, pretty lame. But let's consider this. We're just trying to do an estimate here. And believe it or not, if we calculate the error of this using the 0.05, if you actually put that in your calculator would give you 0.9987 for the sine of 0.05. So in reality, even though it looks pretty lame, if you're pretty close to 0, look how close you are. You only have an error of 0.0013. That's 13 ten-thousandths. That's pretty close. Okay. Now, as we go, though, a little bit further to the right, the error at 0.04 will be 1 minus 0.9210, or an error of 0.079. Okay. 7 to 9 thousandths still is pretty close. Okay. But there was a significant difference between those. So this goes back to remember some of the topics you talked about in AB. That, hey, on your tangent line, the closer you are to that point where you got the tangent line, the closer it's going to resemble the graph. And the same thing with our Taylor polynomials. The closer a point x is to 0, in this case, the more accurate the approximation is. So as long as we stay close to that center, we're going to get a good approximation for this. Let's jump out a little bit and do this one. Suppose we want a more accurate approximation for the cosine of x near 0. Instead of using that linear approximation, let's do a quadratic. Okay. So, in order to do this, we're going to build our Taylor series, and a common way of doing this is just making a table. And since we're doing quadratic, we need to do the term to the 0 power, the first power, and the second power. Of course, if we wanted a third degree, we'd go to 3. If we wanted a fourth degree, we'd go to 4. And we'd have 4 lines here. Okay. Our next column is, we're just going to take the original function and write out its derivatives. This one we're starting out very, very simple because we know that the 0 derivative of this is just cosine. And then n equals 1 would be the first derivative, which is going to give us negative sine of x. And then the second derivative, derivative of negative sine, will be negative cosine of x. Okay. This again, if you needed clarification, this is the f of x function. This is the first derivative. This one is the second derivative. Just to clarify that. And again, if I needed a third degree, I'd have to do the third derivative, fourth derivative, and so on. Okay? And now, in our next column, we're going to do the same thing, but we're going to evaluate this at our a value. Reminder again, since they said near 0, that means our a is 0. That's why I put 0 here. So, cosine of 0, of course we know, is going to be 1. The negative or opposite sign of 0 will still be 0. And then negative cosine of 0 will be a negative 1. Okay. And then what we're going to do is we're going to use all of these to build our Taylor series. Remember, the general term is the nth derivative at a times x minus a to the nth power, all divided by n factorial. And of course, since our a equals 0, we don't even have to write minus a 0 in there. And this term here is each one of these. Okay? So we're going to do a second degree polynomial. Again, I could use an s or a t. I'm going to do a p this time. That's going to equal, remember what it starts out with. We start out with f of a. F of a is just 1 in this case. And then plus, remember the next term is f prime of a times x minus a to the first power. Our f prime of a is 0 times the x minus 0 to the first power, all over 1 factorial. And then our next one will be our f prime of a. Remember, this one is going to be f double prime of a times x minus a squared, all over 2 factorial. So this one, my f double prime, is negative 1 times x minus 0 squared, all divided by 2 factorial. Which simplifies to just 1. This second term goes away, minus 1/2 of x squared, or x squared over 2. Now, watch what happens when I put this one in the computer. And I got my approximation of this by doing p of 0.05. That gave me 0.99875. And when we put in that same value we did before and evaluated at 0.4, what did I get? I got 1 minus 0.4 squared divided by 2 ended up being 0.920. And the crazy thing is that all the way out here to the fifth decimal place, the error at 0.05 actually was 0. Look how close it is. Look over here. They've graphed it for you. Look how close it is to being that exact same graph. If we were to zoom in right here, you wouldn't be able to tell the difference. Okay? And the error at 0.4, again, we're going over here, 0.4 away, is only now 0.001. So not only is it getting closer or staying closer to the center, but if we increase the degree, we will also become more accurate with our estimate. Let's do this for 7 degrees, but this time we'll do our sine of x function. Okay, so again, this is n, 0, 1, 2, 3, 4, 5, 6, 7 rows. This will be our nth degree at x. We're starting out this time at sine of x. The derivative of that is cosine of x. Derivative of that is negative sine of x. Derivative of that will be negative cosine of x. Derivative of that goes back to sine of x. And then it repeats its pattern with cosine of x, negative sine of x, and negative cosine of x. Okay. Again, it says near 0, so our a is going to be 0. So the next column will be our nth derivative at 0. Of course, the sine of 0 is 0, cosine is 1, still 0. Negative cosine will be negative 1. And then we're going to repeat that pattern again. 0, 1, negative 1, and then 0. Okay. So let's do our 7th degree polynomial for this, starting out with our f of a, which is 0, plus 1, that's our first derivative, times, I'm not going to put the zeros in there, I'll just put the x to the first power over 1 factorial, plus 0 times x squared over 2 factorial, plus, next one you'll see is a negative 1 times x cubed over 3 factorial, and then plus, we're going to go back to 0, x to the 4th over 4 factorial, and then plus, oops, I messed up here. This should be a 0 and a negative 1. Sorry about that. Because we're back to a positive 1 times x to the 5th over 5 factorial, and then plus the 6th one is 0 times x to the 6th over 6 factorial, and then plus negative 1 times x to the 7th over 7 factorial. Did I need to write all those out? No, but again, I'm just trying to get you used to the pattern of a Taylor series. Derivative times x to a power over the factorial of that same power. Because this simplifies rather nicely to, even though we say it's a 7th degree, we're not going to have 7 terms because we have 1, 2, 3, 4 of these terms that will be 0. So this just turns into x to the first power minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay. And it does say write a general formula. I've kind of run out. No, I'll fit it over here. The general formula for this, if I wanted to write this for each term, I guess I could. You'll see that it does alternate here, doesn't it? Which means I need to have a negative 1 to the nth power. And then this is 1, then 3, then 5, then 9. So it's actually going to be an x to all the odd numbers. And if you recall, we do 2n plus 1 to give us odd numbers. And since that's our exponent, then the 2n plus 1 in parentheses, factorial, will be our denominator. That's the general term, and we could write it as the summation from n equals 0 to infinity, and that would be the Taylor series for this sine of x. Okay. Let's do another one down here. This one says, let's do e to the x. Oh my goodness, 10 of these? Oh my goodness. Must be calculus. So 0, 1, 2, but wait a second here. If I take the derivative of e to the x, what do I get? E to the x, e to the x. I'm just going to do this 10 times. I'll still get e to the x. This one still says that we're about x equals 0, so our a equals 0, which means, oh, this gets rather boring too, because what's e to the 0? 1, 1, 1, 1, all the way to 1. Okay, so remember, this is giving us that derivative portion of our partial. So let's go this one. We start out with the actual value of 1, and then this will be 1 over 1 factorial times x minus 0 to the first power plus 1 over 2 factorial times x minus 0 to the second power plus 1 over 3 factorial times x minus 0 to the third power plus, which obviously is going to simplify to just 1 plus, and I guess I should have shown that I'm stopping here since this is the 10th, 1 over 10 factorial times x minus 0 to the 10th power. So what's this simplified to? X to the first plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 all the way up to 1 over 10 factorial times x to the 10th. It does say let's write a general formula for this. The general formula of any degree would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. The general term would be x to the n, not just the odd ones, this is all of them, over n factorial plus dot 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 forever and ever. And if we write this in summation notation, this will be n equals 0 to infinity of x to the n over n factorial. Pretty nifty. All right, we did some really, really easy ones. Let's try another one. What if we do the natural log graph and try and write a polynomial for that? Okay. Oh, this time it says near 1, which kind of makes sense because natural log graph at near 0 is going to be infinity, right? So in this case, our a value is something other than 0 this time. Okay? So let's start out with our table over here, starting with 0, 1, 2, 3, 4. Since it says go to the 4th degree, we're going to have to do that many derivatives. So we're starting out with the natural log of x. We know the derivative of that would be 1 over x, or x to the negative first power. Now think about the derivative here. We're going to have to bring that exponent down and then subtract 1 from it. Exponent down, multiply it by negative 1. That'll give us a positive 2. Subtract 1 and get a negative 3. Negative 3 times 2 is a negative 6. And then negative 3 minus 1 would be negative 4. Now we're going to evaluate each one of these, not at 0, but at 1 this time. We know the natural log of 1 is 0. 1, the reciprocal of 1 is still 1. Square 1, reciprocal of that, and then the negative would give us negative 1. 1 to the negative third power is still 1, times 2 would give us 2. And then the same thing here. 1 to the negative fourth is 1, but times negative 6 would give us a negative 6. Okay. So, let's match this up and write our polynomial. And this will be 4th degree. I'm going to start out here with 0 plus this guy right here, 1 over 1 factorial x minus 1 to the first power plus our next one, negative 1 over 2 factorial x minus 1 squared plus the next one is 2 over 3 factorial times the quantity of x minus 1 cubed, and then plus a negative 6 over 4 factorial times the quantity of x minus 1 to the 4th power. And so again, each one of these guys are to the power. That's that general term there. All of these are here. Negative 1, 2, negative 6. And then in our general formula, this is over 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. Those have to match these numbers here. That's the pattern of our Taylor series. If I wanted to simplify this a little bit, I'd get rid of that 0, and then you can see this is just x minus 1 minus the quantity of x minus 1 over, or squared, over 2, and then plus, and then think about this, 2 divided by 3 factorial will just leave us with 3 in the denominator. And then, kind of the same thing here. We know that 6 is 2 times 3, and of course 4 factorial would be 1 times 2 times 3 times 4. Boop, boop. So this becomes the quantity of x minus 1 to the 4th over just 4, not 4 factorial. So we can write a general formula for this. At or near x equals 1 by saying that an nth degree polynomial would start out with x minus 1 plus the, minus, got a minus there, x minus 1 squared over 2 plus x minus 1 cubed over 3, and then minus x minus 1 to the 4th over 4, which means our general term would have to be alternating, and then x minus 1 to the nth power all over n. I did have to put this as an n plus 1. Always check to make sure you're alternating the right ones. We know that this has to be when n equals 2, we need this to be negative, so we're going to have to make sure we add 1 to each one of the even ones to make sure that those are odd and we get a negative, and of course add 1 to the odd ones to make sure this is even and we get a positive value out of that. Okay, so again, key thing here is the higher the degree of our Taylor polynomial, the greater we are to our approximation. And just a reminder to you, sine is an odd function. And if you'll notice from the previous page, when we did our sine, we ended up with first power, third power, fifth power, seventh power. So it can be modeled by an odd polynomial. And then when we did our cosine, remember cosine is an even function. Remember the idea of cosine being able to be reflected, whereas sine, you had to do a spin to get it. And of course, when we did our cosine, look up here, we had that one, where did it go? This one right here. Everything was an even power. To the 0 power, to the second power. If we did the next term, it would be to the fourth power. Pretty awesome? All right, I'm going to skip that last one because